Guys, here's some more things about radicals. Once you know how to reduce them and manipulate them and make them as simple as possible, as I said in the last video, this leads us to be able to start to do things with them. A lot of times when we first look at them, it doesn't look like there's much you can do with them. They look like numbers that are so far off from each other. But as we start to simplify them, we usually start to see a pattern or a trend happen. We start to get something that's called like radicals, or your radical symbols are exactly the same, like square root of 3, square root of 3. And in honesty, we can look at this something like just like we did at the very beginning of the year when we were combining like terms. These are called like radicals. And so, look at this. If I were to just substitute this out for x's, think about this from the beginning of the year, right? If I had 6x plus 3x, how many x's do I have here? You have 9 x's because the x is the same. No difference here, guys. When you have radicals like radicals, remember, you can combine like terms. What's part of this term is a radical, like a grouping symbol. Saying I have the square root of 3 and I have this many square roots of 3 and this many square roots of 3. So how many total amounts of square roots of 3 do I have? I have 9 square roots of 3. You just combine like radicals. However, they don't always give it to you this easy. A lot of times they'll give you a larger radical that can reduce, and then you can see those like radicals. So you have to be careful, have to use those skills from the last video. Let's see as they slowly make these more complicated. Oh, look at this thing. 3 terms. And at first, it doesn't look like these things have anything in common. Oh, I have a radical 125, a radical 5, a radical 2, right? Some of them will combine in the end. Some of them won't. And you have to see what's going on here. Well, I can tell you this. Remember, 5 is a prime number. The only things that go into 5 is 1 and 5. So there are no perfect squares that'll go into 5. Is there a perfect square that'll go into 125? Yeah, there is. And here's a hint to try to maybe think if you don't see it right away. It probably is going to have something to do with one of these radicals. If you were to take 125 and divide it by 5, we end up with 25. And lo and behold, 25 just happens to be a perfect square. So that's the key to this, is you're trying to make like radicals so that we can add them and get rid of them, combine them, make them smaller for us, okay? So let's write this, rewrite this. This is 25 times 5. Well, if we take the square root of 25, we end up with 5. Square roots of 5. Nothing we can do with this 2, so the 2 can come down. This comes straight down to square roots of 5. And like that, do we have any terms that we can combine? Yeah, these two. If you have 2 square roots of 5 and 5 square roots of 5, we end up with 7 square roots of 5 plus 2. Because again, that comes down. And that's your final answer. You just simplify this. Something that was 3 terms simplifies into only 2 terms. Makes it easier for us. I'm going to keep going here. Oh, look at this. Subtraction. Guys, it works the same way, right? If you have 21 of these, and these just happen to be square root of 2, and you take away 24, so you're starting off with 21, and you're subtracting 24, we end up with negative 3 square roots of 2. That's how it works. Easy peasy. But now we have 3 terms we're dealing with. Again, let's take a look at this. 7, prime number. 3, prime number. 112. I bet that reduces. That is either going to reduce 7 times something is 112, and that other something is going to be a perfect square, or it's the 3. I wonder which way it'll be. Check it. Start off with 112 divided by 7. We get 16. 112 divided by 3 gives you an irrational number, 37.3333. So we know it's this one here. So we can rewrite this as minus square root of 16 times 7. Well, the square root of 16 can come out front. Square root of 16 is 4. This whole term comes down. So it's kind of like legal cheating in this problem. We use these other roots to help us figure out that 16. Do we have any like radicals? Yes, we do. Look, these are like radicals. These are like radicals. This is a like radical. 3 minus 4. Okay, that's going to give us what? -1 square root of 7 plus 3 square roots of 3. And that is as simple as we can get this one, guys. It doesn't get any simpler. While it doesn't look super clean, because first time we're really working with radicals, it's not horrible. Okay, we'll see this pops up in our quadratic equation when we solve quadratics that have a root in the answer, because they're not the pretty ones that have a nice pretty discriminant, but sometimes that discriminant can reduce and we have to do that. So we have to be careful with these. We will see these again, maybe like the next video. And here we go. Of course, it wouldn't be anything else without division, right? We got to see, can we divide this? Let's see. 216. We got to figure out which of our perfect squares goes into 216. We're trying to reduce that. 216 divided by, let's start 81. Nope. 216 divided by 64. Nope. 216 divided by 49. Notice, I'm just going down the line. I'm trying to grab all of them. 216 divided by 36. I found it. That's 36. This turns into the square root of 36 times 6. And I can take the square root of this, so this can come out front over 4. And now we can say, let's rewrite this so it's a little cleaner. 6 square roots of 6 divided by 4. What we need to look at now is this. Can this reduce? Yes, it can. If you put this in your calculator, 6 ABC 4, you should get something like this, the 3 over 2. It reduces. Or you could say, okay, 2 goes into 6 3 times. 2 goes into 4 2 times. So you can reduce your coefficient of your radical with the denominator. Boom, you're good to go. That's as simple as it gets. 2 more examples to do. Now we're dealing with multiplication. So multiplication, the rule for multiplication is when you have multiplication, you multiply the outsides, then multiply insides, and reduce. That made massive letters. Here we go. Right like that. Multiply the outside, then multiply the inside, and reduce. Look at it. This is even easier because look, what's outside of this radical? A 1. What's outside of this radical? A 1. So we have a 1. 3 times 7 is 21. And think of the factors of 21. 1 and 21. 3 times 7. That's it. There's nothing else you can do. You are done. Radical 3 times radical 7. The outsides multiply, you keep a 1. 3 times 7 multiplies 21. It can't be reduced, you're good to go. Let's drag this down again so we can keep seeing this as we look at our next problem. Multiply the outsides, then multiply the inside. So outside, we have what? 2 and 4. So 2 times 4 is 8. 7 times 10 is 70. Then all we have to figure out is there a perfect square that goes into 70? Let's see. It's not going to be 64. It's not going to be 25. Let's try 16, maybe. 70 divided by 16. No, that doesn't work. Maybe a 70 divided by 9. No, we're running out of options here. 70 divided by 4. And so we don't have anything. That's it. Again, you are done. This was easy peasy. They didn't even give us any that were hard. So like that, you are good to go. Okay? Guys, just take your time. Be careful with these. It is as easy as what we were doing the last one. Yes, we use the reducing, like terms when you're adding, like radicals when you're adding and subtracting. When you multiply, again, multiply the outsides, then the insides, and reduce. And next lesson, we're actually going to use these in practicing using the quadratic equation again, solving radicals. Amazing how all this stuff just keeps coming around and we keep using the same stuff over and over and over. All right, get out there, guys, get that homework done and finish it all up. Do your EOC review.